So in this video, we're going to actually get to the hydrodynamics part of the solving the problem. So just as a refresher, we first defined the finite element structural model. This was in the file eigen.txt. And we made sure that that input was correct. In other words, the structural model was correct. We then created the reduced basis and determined how many modes that we wanted to use in our hydrodynamic analysis, hydroelastic analysis. And very shortly, we did some processing to get the data into the format that we needed for the hydroelastic analysis. Then we had to take a little bit of a detour because we needed to determine the hydrostatic stiffness. And as I said in that video, that's an optional step. It's required if you want to use the full formulation that I talked about in the lecture series on the theory. You can skip that if you don't want to do that, as I mentioned, or if you're importing the results from another structural analysis program, you're going to probably not be able to do that either. So now we are at the situation of calculating the hydroelastic response. But before we jump into this, I want to point out something, and I kind of meant to do it earlier, but now's a good time to do it, and I didn't do it then. But so these files are actually quite reusable for a number of different similar analyses. So if you're doing a hydroelastic analysis, that's very similar to what we're doing here. And I'm not talking about the structure being similar. I'm talking about just what the steps you want to go through. If they're similar, then these files can be reused, and that's actually definitely what I would do. I would be reusing these files, and they would only require a little bit of modification for the most part. So for example, if we look at eigen.txt, let me open that up here. So some of these things are going to be fixed, right, or changed depending on what model, what structure you're solving. This is clearly the FEA mesh.txt file. The file where we're defining the actual mesh, that's of course going to be very different for a different structure. It almost goes without saying. But a lot of this other business here is very similar, or if not the same, just require a little bit of tweaking. And the other thing is I want to point out is that we have broken down this process. And let me go back to that workflow document. We've broken this process down into steps, oftentimes with a single file for that, input file for that step. And the reason we've been able to do that is through saving the results from a previous step into that date.db file, the database file, so that the next step, the subsequent step, can read that data and pick up for where the previous analysis left off. And it makes it very convenient for us to be able to make sure, do error checking and make sure. A lot of times there's some iteration involved in these. There's typos, there's whatever, and so you don't have to redo everything as you work through it. It's broken down into pieces. So I'd like to encourage you to use these files as appropriate. I think they'll make your life a lot easier. So let's look at this file here and see what we're doing. All right, so this is the hydro.txt file. So as I mentioned, we're going to be picking up where we left off with the eigenvalue analysis. We've already calculated the reduced basis that we want to use. And so we're reading in that database from that file. We don't need to read in the database from the hydrostatic stiffness analysis because we're going to read that file, the result, that hydrostatic stiffness, in separately. And here, this is just some input parameters that I'm defining. So symmetry says we're not, 0 means we're not going to be using any symmetry in this analysis. I'm defining this parameter number mode R as the value 6. What it says is the number of rigid modes is 6. Now this variable name here is whatever you want to give it. I gave it number mode R. Number modes was already defined. We had defined that previously as 18, if you'll recall. And so we know that the number of rigid modes are 6, and so the number of flexible modes is just going to be 18 minus 6 equals 12, and that's just calculating that. Rather than putting it in directly, in other words, defining in mode F equal to 12, this will allow this file to be reused for different problems where number modes is different than 18. This gauge value equal to 2.5, we'll see where that's used. 2.5 is just a default value. I don't believe I've ever really used anything but that. Gravitational acceleration due to gravity, 9.81 meters per second. Fluid density of water. Depth is the water depth, and so I typically use 5,000 just as a number for deep water. So if you want to do deep water, you just need to give it a value that's large enough so that the program is, for the wavelength involved, the program is going to be using the deep water option. So if you think back to the naval architecture lecture, there's an inertial coordinate system and then a body fixed coordinate system. And what I'm saying here is that the body fixed coordinate system, the origin of the body fixed coordinate system, the z coordinate of that is going to be 0.5 in the inertial coordinate system. This says that the position of the center of gravity in of the body in the body fixed coordinate system is at 0. Well, we know that the CG is 0.5. We define the problem to be for the CG to be 0.5 meters above the still water line. So the origin of the initial coordinate system is at the still water line. So we know that the CG is 0.5. So that tells us that ZCG in the body fixed coordinate system is 0. I specifically put the body fixed coordinate system at the CG. Normally, that's where I put it. It's not required, but that's normally where I put it. This says, okay, we're going to look at 4 wave angles, and we're going to look at 67 frequencies. That's a lot of frequencies, but this was a problem, remember, that I did for as a benchmark for people to use, and so I wanted to use a pretty fine gradation in the number of frequencies. All right, so now we need to define the rigid body mass matrix. Now, we could use, if you'll recall back in the eigen .txt file, we issued the mass summary command to confirm that our structural mesh was giving us reasonable results. And we saved then the 6x6 mass matrix that the program calculated from the structural mesh. And I could use that here, but what I'm actually doing here is I'm going to redefine or define the rigid body mass, the 6x6 rigid body mass matrix for the structure based on the quote-unquote analytical results. I mean, this is a simple structure, so it's relatively easy to calculate the 6 inertial values. So I'm inputting a matrix that I'm calling hyd_r mass for hydrodynamic rigid mass. It's a 6x6, and here are the here are the values. So it's a diagonal matrix in this case because of symmetry and principal axes. The 3 masses are the same, and then this is the rotational inertia in the x-axis, rotational inertia about the y-axis, and rotational inertia about the z-axis. Again, I could have just used this value here, this matrix here, but I chose to put in the quote-unquote exact values. All right, now I'm defining the wave angles and the wave periods. So the default is for input to be in wave periods, and even though it says frequencies here. So these are the wave angles, 0, 30, 45, and 90 degrees. And these are the wave periods. And I'm starting at 2-second waves, which is very short, and going all the way up to an 18-second wave here, which for this structure is sufficient, but for other structures you may need to go much further than that. Okay, and that's pretty much the end of this kind of inputting parameters. So the next command is hide parameters. So every command that is strictly related to the hydrodynamic analysis or hydroelastic analysis begins with a hide, HYD, and then an underscore, and then the command, the rest of the command name. So hide parameters defines some parameters we need for the hydrodynamic analysis, hydroelastic analysis. So I use the symmetry, I specify the number of rigid modes, the number of flexible modes, the gauge length, which I mentioned before, the water depth, gravity, and rho. So that's where I'm using those values. And I've defined them as constants up above just for convenience, so that I can just change them up there if I want to change something. For example, if I want to look at different water depth, maybe 500 meters or 100 meters, then I could easily change it up there, and that wouldn't have to make any other change. Then I need to get the coordinate systems defined, and so I define with this hide coord axis command the location of the body fixed coordinate system and the location of the CG. Now we need to define the panel mesh, the hydrodynamic panel mesh. Here I'm converting the FEA mesh to the panel mesh. And this command, if it's applicable, if you've defined within Hydran XR the structural mesh, then it's a pretty convenient command to use to just convert that mesh to the panel mesh. And so that's what I'm doing. One could create, and one would have to go back to the input manual, the reference manual, to understand how to do it. But one could input the nodal coordinates for the panel nodes, the connectivity for the panel elements, and from more similar to what we did for the finite element mesh. But this is an easier approach if it works for you. So what this command does is it takes the finite element nodes and creates hydrodynamic nodes, if you quote unquote, and similarly it converts the shell elements to panel elements. So I print the hydrodynamic nodes and I print the hydrodynamic panels here. Again, that could lead to a lot of output, so you may want to comment those commands out or not. It's up to you. Now this is a very important step not to forget and not to skip, and that is hide body check command. And that's going to calculate and print some very basic information about the panel mesh. So we do need to check our panel mesh as well, just like we checked this structural mesh. We need to check the panel mesh, and this command will generate some results that are consistent with our panel mesh. And so I'm going to, just as we did before in the eigen file, I'm going to uncomment this return so that we can look at the results from hide body check and make sure that our results are consistent. So I'm going to save that, and then we're going to go and we're going to run Hydran. So I've already ran this problem before, so it's populated here. It's the last problem I ran prior to making this video, so it shows up pre-populated there. I'm going to resize this window and put it over here. You know, I think I'm going to do something else. I'm going to also export the hydrodynamic panel mesh just for checking purposes, so just to illustrate that. You know, obviously this has been very well vetted, and so maybe you don't need to do it, but I'm going to do it here just for demonstration purposes. So I've added this line here, which is going to export the panel mesh to so we can view that. So I need to save that and then come over here, type in file in, and we're good to go. So let's view that mesh before we do anything else. So we're going to, let's see here, hydro mesh. So let me expand this, and one of the reasons I wanted to do this is to illustrate something. So you notice now that we're seeing inside the box, and the reason is because when we define the top deck, we define those panels not to be exposed to fluid, and so they're not exported. Only the panels that are the only panels that are exported are the ones with the face equal to 1 or minus 1. And so we have the bottom hull, and we have all the sides and the front and the stern, the bow and the stern. And of course we can, rotate this and look, and what's kind of nice is that the wetted surface, what it thinks is the wetted surface, is green, and so that kind of highlights that. So this is what we would expect, right? And so, but remember, the water line is only halfway through here. We're going to get to the implication of that in a minute here. But when we defined the side elements, we said they were all supposedly exposed to the fluid, but we know that the ones, and the program knows that the ones above the still water line are actually dry. So I'm going to close that. I'm going to quit Hydran for right now and look at the .out file. So if we come over here to the .out file and open that up, let's go to the top. Of course, this is just repeating the input, right? Now this is here, I wanted to talk about this. This is the hide convert FEA mesh. So that we don't have any interface elements in this mesh. So it's reporting that it found 0 of those. It found 1880 wet quadrilateral shell elements and 0 wet triangular shell elements. And then it's converted with the finished conversion. So it gives a panel summary here, kind of repeats some of this information, but it says it processed a total number of 1,880 panels. All of them were quadrilateral panels. There are no triangular panels in this mesh. So, and now it says that there are 1,440 wet panels and 440 dry panels. Those 440 dry panels are the panels on the sides and the front and the stern, the bow and the stern, that are above the still water line. And the program knows that those are dry panels, and it's not going to do anything with those. It exports them into panels, but the program is going to ignore them for any hydrodynamic calculations. Then, as I mentioned, I print the nodal coordinates. That generates a fair amount of output. So I'm going to skip that and skip down to where I'm printing the panels. And again, this generates a fair amount of input. So I'm going to skip that for the most part too. But I did want to indicate here that there's a wet dry code here, and it tells you whether the panel is wet or dry. All right, so here are the results of the hide body check command. So it checks to see if some nodal coordinates or not would violate some symmetry. There's no symmetry in this case, or we're not exploiting symmetry in this case. So there are none reported. So the first check is it's calculating the volume, the displaced volume of fluid. And this is an important check to make sure that your mesh is correct. I mean, the volume of this structure, the displaced volume of this structure, is very simple to calculate. It's just a rectangular box. And so, and we get the exact value because it's so easy to calculate. You can expect some variation here between say your estimate or your calculations with other means and what's calculated here, because this is calculating these values numerically based on the panel mesh you've specified. So if there's, the accuracy is typically going to depend upon how fine a mesh you're using. But this is in this case spot on. And similarly with the total surface area. The next set of numbers are the center of buoyancy and inertial coordinates. And we know that the center of buoyancy is 0.5 meters below the still water line, just from the box. And that's exactly what is calculated in the program. And so that's a good confirmation. And also we know that the center of buoyancy is at 0, 0, and the XY coordinates are 0, 0 in the inertial coordinate system. Similarly, the input coordinates for the center of gravity, this was input, remember, so it's at 0.5, is above the still water line. So the difference between the centers of gravity and centers of buoyancy is another check. Just obviously anybody could subtract these to get it, but it's a check that's for convenience here. And we know that the center of gravity is a half a meter above the still water line. The center of buoyancy is a half a meter below the still water line, and so there is a meter difference between the two, and that's what's calculated by the program. The other thing that's very important is, remember, is that the center of gravity and the center of buoyancy have to be on the same vertical line for a freely floating structure, and that's what's calculated here. So we're confident, at least in this, with these basic checks, that the mesh is acceptable. So now we can come back here, and I'm going to comment out that mesh command and comment out this return, and then we can come down and start looking at what the next steps are in this analysis. So first we're going to define the rigid body modes, and so they're just the traditional 6 rigid body modes for this structure, so there's no parameters involved to this command. And then we're going to define the hide flex modes, but remember we've already defined those and we wrote those to a file. We saved those in an array called .phi in the database. So this command is telling it, okay, the modes are in .phi. And it knows that the first 6 modes are the rigid modes, so it's going to assume that the modes 7 and on are the flexible modes. Now we know that the mode shapes are mass normalized, so the identity matrix, the modal mass matrix is just the identity matrix. So I'm going to define a matrix called hyd_mstr. It's the mass matrix for the structure for the hydrodynamic calculations, and it's a number in modes by number of modes identity matrix. Now, one thing we've done differently here is we have substituted the mass normalized rigid body modes with the sort of traditional unit surge, unit heave, so forth modes for the rigid body modes. And so the mass matrix associated with those modes, those 6 modes, first 6 modes, is not the identity matrix. It's the matrix we already defined. And so I'm putting that matrix, that hyd_r mass matrix that we defined earlier, into the proper location in hyd_mstr. Okay, so now we've got the structural mass matrix defined. Now the structure stiffness matrix, remember, is because we've mass normalized the mode shapes, the structure stiffness matrix is just going to be the frequency squared, a diagonal matrix with the frequency squared. And so that's all I'm doing here. I'm putting the frequency squared into a matrix called hyd_kstr, or structure stiffness matrix. All right, so we've got that done, and the next step is the hydrostatic stiffness matrix. Now, we can either keep the hydrostatic stiffness matrix computed by the previous commands, hyd rigid modes and hyd flex modes, or we can use the one from the hydrostatic stiffness calculations that we did earlier. So even when I use the hydrostatic stiffness formulation, typically I use but not always, but sometimes I replace that upper 6x6 with the exact results from the hydrigid modes command. The reason is because those are going to be exact, and there's going to be numerical errors in the other one. But in what this, I'm not doing that here. I'm just using the hydrostatic stiffness matrix that we calculated earlier. Remember, we wrote that to a file, so I'm just reading in that file and putting it into .hydkf _kf. And then we're not going to have any damping in the structure stiffness matrix, or the structural damping matrix. So I'm just zeroing out. We just still need to define it, but we're zeroing it out. And then I print each of those just for to view what we've got, just to confirm that the numbers are what we expect them to be. All right, so the next command, hyd_analysis, calculates the added mass, damping, and exciting forces. It doesn't calculate any response because that has been separated out from this command. So there's two different commands, one to calculate the added mass, damping, and exciting forces, and the other one to determine the modal response based on those added mass, damping, and in this case wave exciting forces. The reason is because the added mass and the damping are going to be the same whether they're not dependent on waves, so they're dependent on the motion of the structure. So they're the same whether the exciting forces, what's exciting the structure to move, is either coming from waves, which it is in this case, or say from seismic excitation, if we've got that kind of a problem, or any other harmonic kind of forces. And so the program can do all of those, and so that's why it's separated out into two separate steps. There's another advantage to doing that, because if some parameters change, for example, if you want to modify mooring stiffness, for example, you don't need to recalculate the added mass, damping, and exciting forces to look at, say, a parameter study on the effect of different mooring stiffnesses. You can reuse those same added mass, damping, and exciting forces. Just define the mooring stiffness and redo the Hyde analysis response section of this. But in this case, we don't have any mooring, and so we're not we don't have anything like that. So then we're saving the results for future use, and we're saving that database so we can use it subsequently. All right, so let's run this whole thing. Remember, there's 67 frequencies here, so I may this is a new computer, so it's the latest and greatest, so it may be pretty fast, but I suspect I'm going to have to kind of do a stop it and then pick up after it's all done, so that we don't sit there watching this thing run. So I forgot to save this, so I don't want that messing up my output file, so I'm going to just start a new project and just give it the same name. And all right, so now it's doing the wave frequencies, so it's pretty fast, but we're on frequency 3. We've got 67 to go, remember. So I'm going to pause the video and come back once it's finished. All right, it's done with its calculations. So I would like to point out that the let's get back to this guy. The Hyde analysis response process is very, very fast. The most computationally intensive part of all of this is calculating the added mass and damping, the Hyde analysis. So, and I've saved the database here, and it's been loaded into the GUI. So that's done over here by, selecting reload database. So if we look at what's in the database, we can look on the left, but we can see that there's about 59 megabytes. So the GUI is a little slower, well, substantially slower than the computational engine is about dealing with quasi-large amount of data. So I wanted to go through this and highlight a few things here. So dot hide add_im is the added mass. So the added mass matrix is 18 by 18 because we're using 18 modes. And then there's one matrix for each frequency. So, and it's a real matrix, of course. And similarly, the damping is an 18 by 18, one for each frequency, and it's also real. The diffraction forces and the incident forces, there's one force per each degree of freedom, each mode, and there's going to be one for each wave angle and one and frequency. So it's an 18 by 4 by 67. They're both that, and they're complex. The response we're solving the equation of motion for the generalized coordinates. So the generalized coordinates are calculated are stored in this array .hide gencore, and there's going to be 18 generalized coordinates, and we have one for each frequency and wave angle. So it's also complex. And I think that's kind of all. Well, okay, so one thing I did want to point out, think about it. Here are the diffraction potentials and the incoming potential and the radiation potential. These can be a little on the large side, so if you don't need them, you can delete them. Just make sure you don't want them in the future. And of course, they're complex as well. So I got all this by using LL, which is shorthand for long listing. LS would give you this kind of listing here, where it doesn't tell you it's more compact, but it doesn't tell you the type of array it is, real, complex, integer, whatever. All right, so we've saved the results to the database file. And if we come back over to this guy, the next step is to start calculating the additional responses. We've calculated the generalized coordinates, but yeah, they're interesting to look at to see which modes are being excited. But for displacements and stresses and so forth, we need to do some post-processing. So from here on out, most of everything we're going to be looking at is doing post-processing. So we've done the heavy lifting, so to speak. We've defined the structural mesh, the fluid mesh. We've solved for the stiffness, the stiffnesses, the added mass and damping and exciting forces. And then we solved the equation of motion. So now it's just an issue of extracting the results that we want. So the next step is to do some post-processing, preliminary post-processing, and that is we need to set up a so-called modal matrix, which will allow us to calculate the transfer functions, and specifically the most challenging part is the transfer functions for stresses. So we're going to take a look at that in the next video.